So today we're going to talk about limits involving infinity. So far in this class we've talked about when a limit approaches a number, and then your limit's been equal to a number or it doesn't exist. In this situation, our limits are either going to approach infinity or the limit will be infinite. So there's going to be, your solution to the limit is infinity. So let's start by thinking about the two different ways we deal with infinite limits. So the first way is when we think about supply and demand of any situation. So when we think about supply and demand of a population, so if we think about like supply and demand for the number of teachers. Okay, so some population, doesn't matter what it is, they always need 2,000 teachers. Okay, so over time, the number of teachers will increase, decrease, increase again, decrease again. So say we need 2,000 teachers and our supply level is right here. So what's going to happen is a whole bunch of people are going to graduate from college. They're going to think, oh, I can be a teacher because they need them. So all these people are going to become teachers, and then there's going to be an influx of teachers. So there's going to be too many. Some people are going to leave, some are going to retire. Oh no, we don't have enough teachers again. So then more people are going to become teachers, and then more people are going to retire. And this will continue on and on and on and on and on. And eventually it'll level out. But you're not going to see it leveling out. It's never going to be exactly 2,000. It's never going to level out eventually. Our oscillations here are just going to get smaller and smaller and smaller and smaller and smaller. So we can describe this limit as the limit of some function, f of x, as x is approaching infinity. Because our oscillation will continue forever and ever and ever. And just like it has here, it's going to continue, it's going to oscillate, 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 but it's never going to eventually evenly be 2,000 for a period of time. That's just not going to happen, okay? So that's the first type of limit, when x is approaching infinity. The second type of limit we're going to look at is when you have an asymptote involved. So if you have an asymptote, a vertical asymptote, whatever that is, let's say that's 2 pi, okay? So whenever you have any sort of asymptote, your function's going along, going along, going along, oh no, it can't cross it, but it's going to continue all the way up. So your function is never going to end, right? But your x value can't go past 2 pi, because that's our restriction of our asymptote. So we can call this an infinite limit. So we would say that the limit as x approaches 2 pi of f of x is infinite. That's really messy. Hang on. We don't want that mess. Let's make this bigger so I can write. Okay, so our limit as x approaches 2 pi of f of x is infinite. Okay? Also, since we don't know what infinity is, you never, ever, ever want to write this. The limit as x approaches 2 pi of f of x equals infinity. Okay? This doesn't make sense. You can't have something if you don't know what it's equal to. Does anyone know how big infinity is? Because I don't. Don't write that. It's wrong. Okay? It doesn't make sense. Infinity is an idea, not a number. You can't equal an idea. Okay, so let's move on now and talk about the formal definitions of these two types of limits. So, if we move down here. So the first one we're going to look at is the definition as the limit as x approaches infinity, okay? So we're dealing with this first situation of two types of limits, so a supply and demand type of situation, okay? So L equals the limit of f of x if and only if for any number epsilon greater than 0, there is a number d greater than 0, such that if x is greater than d, then f of x is within epsilon units of L. So let's draw a picture. Okay, so this is very similar to the definition of a limit we looked at before, or epsilon delta definition of a limit. So in this situation, we have some function. So we can say that is our function. And we know our function is going to level out at some value here. Call that value of our limit L. Okay. So this definition tells me that as long as I'm within an epsilon value of L, so we can call that epsilon plus L, and we can call this L minus epsilon. So if I always want to be within this range, that will always happen at some point where X is greater than some value D. So as long as X is greater than D, I'm within this range on my y-axis, okay? My limit will always be epsilon away. That's what that definition means. So now, if we move on to the definition of an infinite limit, right? So now we're dealing with when our limit approaches infinity, and there is a typo in this definition. So it should say the limit as x approaches c of f of x is infinite, and this should say if and only if for any number e greater than 0, there's a number delta greater than 0, such that if x is within delta units of but not equal to c, then the absolute value of f of x is greater than e, okay? It's a lot of words, but I promise you can handle it, okay? It's not that complicated once we look at it. So if I move to this side of my paper, and I draw my graph, okay? And I'm going to draw a curve with an asymptote, because I know that's what's going to happen if my limit's infinite. It has to go up to infinity. And my asymptote is at some value c. So let's go ahead and add that in. So at some value c, right? X is always going to be less than that value c, right? X can never equal your asymptote. So at some value c, there is a value of e such that e's corresponding x value is always within delta units of c. So that value there is delta. Okay, so that's what that definition tells me. As long as x is within delta units of c, so as long as x can get really close to c but never equal c, my limit, whatever it is, will be greater than my e value. Okay, that's what it's telling me. So let's go ahead and think about now, could we ever have a situation where x is approaching infinity and our limit is infinite? So let's look at the graph f of x, or let's look at the function f of x is equal to x squared. So if I look at the function f of x is equal to x squared, and today we're only going to look at it for x is greater than or equal to 0. So if I look at this function, I know it's a parabola, so it'll look something like that, okay? So I know that this function is continuous, because it's a quadratic function, and I also know that no matter how big the value is I plug in for my x value, my y value will always be significantly larger than it. So for example, if I just plug in x equals 1,000, 1,000 into my function, I know that f of x would be 1 million. Okay, so 1,000 is a big number, but 1 million is a significantly bigger number. So no matter what value I plug in for x here, my y value is going to be huge. So in this situation, my limit as x approaches infinity of f of x is infinite. Sometimes I find that students find it difficult to understand that even though our x value is going to infinity, we know that this one's also going to infinity, okay? It doesn't matter that this infinity is a smaller number than that infinity, right? They're both huge concepts, okay? I know that can be difficult to grasp your head around, but this infinite is bigger than this infinite, okay? Doesn't really matter, but just things to keep in mind. So let's look now at some special properties involving our infinite limits. So let's look at this first example. So if f of x is equal to 1 over g, and the limit as x approaches c of g of x equals 0, then we need to figure out, or I would like you to figure out what the limit as x approaches c of f of x is. So let's go ahead and write some stuff down. So I know, I'm sick of red. Okay, so I know I have the limit as x approaches c of f of x, and I'm trying to determine what that is. So I know that that limit is equal to the limit as x approaches c of 1 over g of x. And based on the quotient rule of limits, I know that the limit as x approaches c of 1 can be divided by the limit as x approaches c of g of x, okay? And I also know by my quotient rules that the limit of a constant is equal to the constant, which leaves me as the numerator of 1. And I also know that this limit, the limit as f of x, the limit as x approaches c of g of x is equal to 0. So I don't want to write 0 there because it doesn't make any sense, so I'm just going to rewrite the limit. Okay, so that's going to give me the limit as x approaches c of g of x. Now, my limit equals 0, but g of x actually does not equal 0. So let's think about what happens when I plug in a number that's really close to 0 for my limit, but not actually 0. So for example, if I plug in 1 over 0.001, so 1/1000th is really close to 0, so that's great. And if I divide them out, I'm going to get 1,000. Okay, so I have a number that's pretty close to 0, and when I divide 1 by it, I get 1,000. So it's starting to give me an idea, right? The smaller my number is in my denominator, the bigger number my answer will be. So that's 1/1000th is a pretty small number, but let's see what happens when I plug in something even smaller. So if I plug in 1 over 1 times 10 to the negative 8, okay? Sorry, that's an ugly 8. So 1 times 10 to the negative 8. So when I plug that in, remember, negative 8 would mean there's 8 zeros. That would give me 1 times 10 to the 8th as my answer. So the bigger number I plug in my denominator, or I'm sorry, the smaller the number I plug into my denominator, the bigger my answer becomes. So if I'm approaching a really big number, that means that my limit then is infinite. Okay, so let's move on now to look at what happens in our next situation. So our next situation is similar, but instead of my limit of g of x as x approaches c equaling 0, it now is an infinite limit, okay? So we're plugging in essentially a huge number into g of x. So again, if I use my limit definition, I will see, so I'm just going to start from the beginning. So I know that the limit of f of x as x approaches c, if I just skip all the way to my last step, is going to give me 1 over the limit as x approaches c of g of x, okay? So essentially 1 over some huge, huge, huge number. So if I'm dividing 1 by a huge number, so let's just say I'm dividing 1 by 1 million, okay? Or actually, let's pick an even bigger number. So I'm going to say that I'm dividing 1 by 1 times 10 to the 27. Okay, so 27 zeros after 1, whatever number that is, huge, okay? So when I do that division, I'm going to get 0.000 all the way down, 27 zeros, and then a 1. Okay, I have 27 zeros here. So that's a teeny, 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 tiny number, right? It's minuscule. So this limit then would equal an equally microscopic, a minuscule number, which would be 0, okay? So whenever you're dividing 1, or any number, by a huge, huge, huge number, your answer is going to be 0. And if you're dividing 1 by a teeny, 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 tiny number, your limit's going to be infinite, okay? It's pretty self-explanatory. Okay, so my iPad's being weird. So for the back page of notes, I need you to click on the video link that says 2-5 part 2, and that will be the back page.